That's quite a warm reception. Thank you very much. I'm very happy to be here. I've never been here before, and I mean, quite a time in your country's history for me to be here, certainly. Well, they asked me to do, pretty high-level or technical talks, pretty deep technical talks, and I'm hoping that you'll be pleased with what I've come up with. The first talk that I'm doing today is about Windows Store apps and the process model. First, let me just say a quick word that I am from Wintellect. We're a company that does consulting and training services. I'm sure many of you are familiar with me and the various books that I've written, which I show here on the slide. My most recent book is on the far left. This one just came out in December, and it is for, oh, I got caught. Okay. It's for people building Windows 8.1 apps using the C# language. And by the way, if any of you would like to be my Facebook friend, I'm looking for more Facebook friends. So if you want to be my Facebook friend, I will be yours. Or if you want to follow me on Google Plus or Twitter or LinkedIn, I would be happy to befriend any of you on those services there. Down below is the link to the Wintellect blog, where a bunch of Wintellect people post technical content about Microsoft Azure or C#.NET or threading or Windows Store apps and so on. And then way at the bottom is my email address, which you are welcome to email me at. The only thing I ask you is do not send me source code and say, please help me find the bug. I get a lot of that, you'd be surprised, and I don't have time for that. But some other emails, you're more than welcome to contact me. The other thing I'll mention, this is the last piece of marketing before I get into the technical content, is that in June of last year, Wintellect announced this latest service. It is called Wintellect Now. We have taken a lot of the technical content that we have been creating over the years, and we've now been recording it and posting it up on the website as a subscription service. All of you in the conference, we have a promotional code that you could use. It's not this one, although you could use this one as well, and it would give you free access to all the content for 2 weeks. So we encourage you to please go check it out. Hopefully you will enjoy it and subscribe to the service. Okay. There's like singing or something. All right, so now with that out of the way, I will now focus on the technical content for this course. So I have been working with Microsoft technologies for many, many years. And I got to tell you that as far as APIs go and SDKs, I did MS-DOS, I did 16-bit Windows, I did 32-bit Windows, I did Microsoft Foundation Class Library, I did Active Template Library, I did .NET, and of course the latest one from Microsoft is the Windows Runtime. That now started shipping with Windows 8. And of all of the various API technologies that Microsoft has produced, I believe that Windows Runtime is absolutely the best. It is the cleanest, simplest, easiest one to use of all. It's even a little bit better than the .NET framework, I would say. Not massively better, but a little bit better than the .NET framework. And one of the big features about Windows Store applications that I think Microsoft has not done that good a job of explaining to potential users and customers, as well as for software developers like yourself, is that Windows Store apps are secured and they are locked down. So I know for me, I've been a Windows user, as an end user, for many, many years of my life. I mean, also a developer too, but an end user as well. And I have gotten to the point where I've been afraid to install software on Windows because any software you install could go into my documents folder, can get access to any Excel files that I had there, Microsoft Word documents that I had there, where I store all my business documents. And then those applications could go and upload them to a server somewhere where people who run those servers could then get access to my company or personal information, which I don't want to have happen. And one of the great things about Windows Store apps is that they live in this security sandbox that prevents that kind of thing from happening. So users should feel very comfortable going to the Windows Store app and installing applications from the store and knowing that that application can do no harm on their computer. Also, really for the first time in Microsoft's history, the uninstall actually works. And yes, yes. And that's really a big improvement. You know, even when .NET first came out, we used to tell people that uninstall really worked there too. But it really didn't, because if the application put something in the registry or created a file in a folder somewhere, then usually the uninstall programs never got rid of everything. But with Windows Store apps, it's actually true, for the first time ever, that everything actually does get uninstalled. So in this talk here, if you are interested in building Windows Store apps, and I would encourage you to do so because users will have a lot of confidence with those applications because of the security and uninstall, plus a lot of other things I haven't mentioned, then it's really important to you as a software developer to understand how does the process model work. What's actually happening inside the application, the Windows Store application that you are building? How does the system manage the address space? How does it go and create threads? How do those threads create the windows that appear on the screen? And that's what I'm going to be talking about in this presentation here. So I start off by saying that applications have 3 different kinds of threads that live within the process. The first thread that you end up having is what we call the primary thread. This is the thread that Windows has always had since the very first version of Windows, in fact. So an application gets created in a process. The operating system creates the primary thread within that process, and then that primary thread goes and executes your main method. And then your main method does any initialization it needs to do for the process. Now, also within that process, you can have various thread pool threads. And you can use these for various callbacks, I/O operations that complete. If you want to take some computationally intensive work and you want to spawn that off onto multiple CPUs that are in the machine so you can do the work more quickly to get the user a result faster, then we would use thread pool threads for that. The next kind of thread that we have are what we call view threads. Now, this is really somewhat new for Windows, but also somewhat not new. If you're used to building a graphical user interface applications in Windows, like using Silverlight or Windows Presentation Foundation or Windows Forms apps, then you're familiar with this concept of the GUI thread, the graphical user interface thread that creates the user interface, the windows, the controls, the buttons, the list boxes, and so on. Historically in Windows, that has usually been the main thread. So the main thread would become the graphical user interface thread. But with Windows Store apps, that is not the case anymore. With Windows Store apps, your primary thread executes main and initializes the process, and then the operating system creates another thread in your process, which we call a view thread. And a view thread is like the graphical user interface thread. Now, more specifically, or by definition, a view thread, or we have this concept of a view is a window, so that is your drawing surface that goes on the screen, and then it also includes the dispatcher. This is the code that takes window messages like keystrokes and mouse events, and then goes and dispatches them to the window so the window can update its user interface to show the user that it's accepting the input that the user is creating. Now, typically, in a Windows application, there would only be one thread that is the graphical user interface thread. But in a Windows Store application, this is not the case. There can actually be multiple threads that are UI threads, and in fact, that's quite common. So let me show you the 3 different kinds of view threads that you could have. The first kind is what we call the main view thread. There will only ever be one of these inside your process, and it is responsible for creating the main view of your application and for processing all events for that main view. Now, I started the Mail app over here. This is the Mail app that ships with Windows 8.1, and the Mail app is telling me that I have a payment ready. That sounds good. The Mail app has the main thread, which you don't see because there's no user interface to that, but then it has created this other thread, which is the main view thread. That thread has created this window, and the window is filling the entire screen. And there's only one main view for any given application in the system. And any input that I create, if I click on these items over here, then the main view thread is doing all the processing, and it's updating the information on the far right. Now, the main view thread is responsible for what we call processing launch events. So when the user clicks on the tile and launches the app, that's what causes the main view to initially appear. If the user clicks on a secondary tile on the start screen, then that brings the application to the foreground and shows the same user interface that was there before, and then that thread processes the secondary tile. Also, if the application were to pop up a toast in the top right-hand corner, like when a new email message arrives, the user can click the toast with their finger, and then the application comes to the foreground, and it's that same main view thread that processes the toast notification as well. There are some other events that can occur in the system that will cause the application to come to the foreground and for that one main view thread in the application to do the processing. Those are things such as file activations. For example, if the user goes to the File Explorer in Windows and double-clicks on a PDF file, then a PDF reader app will just come to the foreground and its main view will go and process that. Or a protocol. For example, the Mail app supports the Mail-to protocol. Another application wants to activate a Mail-to with a URI, then the Mail application will come to the foreground and its main view thread will do the processing there. There are some other events that are processed by the main view thread as well, but these are far less common, like a device has been plugged into the machine, the user is looking up a contact, a lock screen call, appointment provider if it's a calendar app, and so on. Now, in addition to the main view thread, there can be hosted view threads. Now, there's only ever one main view thread, but for hosted views, these threads come and go. The main view thread lives over the lifetime of the app. The hosted view threads, they get created, they show you a user interface, the user does something with it, and then the user interface goes away and the thread gets destroyed. Now, here's an example of using Mail's hosted view. I'm going to switch here over to Internet Explorer. And here I happen to be looking at the Wintellect Now website. But let's say I would like to take this website and I want to share it with someone else. So we would open up the charms, then I would select Share, and then Windows shows me a bunch of applications that have registered themselves as applications that can share information with other people. Now, if I choose, let's say I'd like to email this to Jeffrey Richter, to myself, then when I select this, the Mail application has a new thread that is created in it, and that thread creates this window that you are seeing right here, and this is what we call a hosted view. The Mail application still has its main thread, or main view thread, if you will, that shows the main app, although the user's not looking at now, so the user doesn't see the main view. Instead, the user has brought this up in a sharing window, and this has created a separate thread. Mail is showing a separate user interface on that thread, which is what you see here. And then I could go and mail this to myself, which I will do. I will do. Then, of course, if I was in another application and I could say I want to share from that application, then another thread would be created to show Mail's hosted view there, and then the user says who they want to mail it to and whatnot. Then the user dismisses the hosted view, Mail mails the message off, and then the thread that created it gets destroyed. Now, hosted views are used for a lot of different kinds of hostings. By far, the most common hosting that you'll find is the share target, which is the one I just showed you, which happens when I bring up the share charm in Windows. There are some other hosting scenarios that can happen where an application can be hosted in a window that's being presented by a completely different application. Those things are like the contact picker, the file open picker, the file save picker. There's a cached file updater, appointments provider for calendaring information. If you have a printer attached or if you have a camera attached, there's a way to get some a hosted view up where you can set printer settings or camera settings as well. But by far, the most commonly used is the share target. Now, in Windows 8.1, they added a new kind of view that didn't exist in Windows 8.0. This new view, I call them an auxiliary view. And this was added because of a lot of customer complaints where customers might be doing some email. Oh, look, I received the mail. So it means the internet's working. That's good. So sometimes you're composing an email that you're going to send to someone else, but you want to look at an email that was sent to you, and you're using some of the information in that email in order to compose the new one you're sending to someone else. So they have given you this new view that was introduced in 8.1 to accommodate these scenarios. So here I am in the Mail app, and if I swipe on my screen, I have this option down here in the bottom right called Open Window. When I click on this here, you can see a new window is created, and the mail message is put into there. Now, what's really happening underneath the covers is that a new thread is being created. We'd call this an auxiliary view thread. That auxiliary view thread is allowed to have a window associated with it, and that would be the window on the right-hand side. The window on the left is still the main view thread showing this window. It's an auxiliary view thread showing the window on the right. And then the application can put whatever it wants to in the contents of that window. Here it's putting the content of the email message over there. But these are two separate threads running in the same process, each thread having its own separate user interface. And then Windows allows the user to resize these any way it wants, and these windows will resize to fill up the whole space that they're allowed to use. So those are, and now I'm going to close it. So those are the three different kinds of threads that you can have. There's, well, I guess it's a little bit more than that. Well, there's the primary thread, there's the thread pool threads, which I didn't show in this example at all. Then there are the view threads. Those are the three kinds. And then there are three kinds of view threads. The main view, the hosted views, which you can have one or many of those, and then the auxiliary views, where you could have one or many of those as well. There's one other thing I'd like to point out here, which is also very different from the way Windows applications have worked in the past. Windows Store applications are always single instance. So if the user comes to the start screen and runs the Mail app, that just reactivates the main view. Right? I could do this all day long, and it keeps coming back to the same place. Whereas previously with Windows, if you had a desktop app, and this is still true for desktop apps today, of course, is that the user can go and start like Notepad, and then if they start Notepad, that runs a whole new instance of Notepad. And then if they start Notepad, that runs a third instance of Notepad. So each one is running in its own separate process. That is not true for Windows Store apps. In Windows Store apps, they only ever run in one process at a time. So it's either not running or it is running once. And then it's just creating and destroying threads within that process. Okay. All right, so now, that is the kind of the high-level overview. Now I wanted to share with you some of the Windows runtime classes that exist so that in your code that you're writing, you have control over these threads and over these views so that you can see exactly how all these pieces fit together. When your application starts running, there is a Windows runtime class called Core Application. This Core Application class manages the process's lifetime, so the lifetime of your application within its process. And it supports suspending and resuming events, which I'll be talking a little bit more about closer to the end of this presentation. Now, as I mentioned here, this is a static class, so you can't create instance of this. There's only one instance of it because your applications are single instance applications. So there's only ever going to be one of these. Now, it manages your core application views, it's called. So your application consists of these views. And you can have a main view, and there's only one of those that you would have for your application. There's a views collection, which is a collection of all the views that are in your application. And then there's this function called create new view. This is the function that you would call in your application if you wanted to create new windows, like I just demonstrated a moment ago with the Mail application, where I created a new window to show the contents of a mail message. Now, this Core Application class, if you are a C# developer, normally you don't work with it directly. In C#, there's a class called Application, which is defined in the Windows UI XAML namespace. And this application class is the base class of your app class, which Visual Studio creates for you automatically whenever you create a new Windows Store application project using Visual Studio. Now, you'll create a class derived from this app class, which is really a wrapper around this core application class. and your application class object will be a singleton. That is, you can only ever create one instance of it. In fact, I tried once to create a second instance just for fun to see what would happen, and the operating system threw a catastrophic exception. Yes, which I had never seen before, ever, and I thought, wow, I will never do that again. It's clearly a very dangerous thing to do. It's funny that they have catastrophic exception. Okay, so as I said, you have this singleton, which represents your application entirety. And then this application has a bunch of views that are associated with it. So that brings us to this class called Core Application View. This is a Windows runtime class, and you will have one instance of this class for each view that your application currently has alive within it. And it raises events like the activated event. So whenever the view is being activated and shown to the user, this event is raised. So then you can have a callback method registered with this, and this would be a place for you to update the user interface because you know the user is activating your UI. There's a property here that indicates whether the view is a main view or a hosted view or neither. Neither would mean it's an auxiliary view, like I showed that mail app a moment ago. And then a view, as I said a moment ago, or on the previous slide, a view consists of a window, and it also consists of a dispatcher. Those two things together is what we refer to as being a view. Well, a window, or a core window, is your drawing surface. So your thread will have this core window, and that will fill the entire space that Windows allows it, and that is your drawing surface. And then you can put anything into that drawing surface you want. Buttons, text boxes, list boxes, and so on. Or of course you could draw pictures if you're building a game, just set the colors of the pixels however you desire them to be. And the core window, it raises various events too, like pointer events, if the user moves the mouse or if the user touches on the screen. Key events, if the user is typing onto the keyboard, and that is the window that is currently active, that has focus. Size changed events, visibility events, and so on. Now, if you are a C# developer, then C#, or there's a class that you would use that's in the XAML namespace. Windows UI XAML .windows. And this class is a sealed class that is derived from core window. So as a C# developer, you would tend to use this class, but this is really a wrapper over the Windows runtime class called core window. In the XAML world, this class, as I said, is a wrapper around this, and it adds one additional property. And the property that it adds is called content, and the type of that property is UI element. And this is how the XAML world integrates itself in with the Windows runtime drawing surface. So when you are creating your XAML controls, they're all derived from UI elements. And to take your XAML user interface tree and then to put it into a drawing surface, you just take the root of your UI tree, assign it to the content property of this window class, and then it does the work of rendering the XAML UI tree into the drawing surface that is given to you by the core window. Then there's this other class called Core Dispatcher. And as I said, a view consists of a window and a dispatcher. The dispatcher is the message pump. It is the thing that can take all the window messages, like keystroke messages, touch messages, and so on, and then call callback methods to say, the user hit this key on the keyboard, the user clicked over here with the mouse. And then you can register callback methods with those things, of course, to execute code in response to those user interface events that are occurring. All right, so now we've got to the process. The process has these threads. The threads have these views, and then the views we're going to put into them XAML, and that's how we're going to draw our user interface on the drawing surface of the view. Well, that brings us now to the XAML page navigation. So what they recommend, and this isn't necessarily going to be the right thing to do for all applications out there, but a lot of applications out there have a navigation model where you show the user something in the user interface, and then the user can click, and that takes them to something else in the user interface. And the user can click, and that takes them to something else in the user interface. And then, of course, the user can go back to previous things. In fact, I built a little app Now, I am a horrible user interface designer. This is not my forte at all. But this is an app that I wrote, thank you very much, and yes, thank you. Thank you. And the user interface is embarrassing. However, it does a lot of really good stuff, and it demonstrates a lot of the underlying technologies that I've been talking about. And not having a pretty user interface helps you to focus on the things that are really important. Okay, so this application, I've just started it. And you are currently looking at its main view, provided by the main view thread. And I say over here that we are looking at page 0 of the app. Now, over here, I can see why the application was activated. It was a regular launch activation, which means I just clicked on a tile on the start screen, and that's what brought it up. Now, I do give there's a text box here, and I give the ability for the user to enter something into the text box. So why don't I'll enter my first name. So I'll just put Jeffrey over here. Now, the user can go from here, and they can drill down in my application to another page. And they do that by clicking this button. By clicking this button here, I'm now going to go to page number 1. So as you can see, page number 1 is here, and I passed some data from page 0 to page 1. You'll notice that this says Jeffrey in the top. The way my app works, I take whatever is put in the bottom text box, and when you go to a new page, I put it into the top text box. So I'll do it again. Over here, I will put in my last name, Richter, and then I will click over here, and now I'm on page 2, and you can see Richter is up here at the top. Now, the user's been navigating down in this app, but the user wants to have the ability to maybe navigate backwards. So I have a back button, and if they click back, we go to page 1, where you can see Jeffrey and Richter, and if they click back again, they come to the main view launch activation with Jeffrey, and of course, I let them navigate forward as well, right? And then here's the end, so they can't go forward more unless they put something else here. How about I put Kiev? And then I go to page number 3. Okay, so this is a typical design for a Windows Store application. So now we're going to talk about how to actually implement this typical design. Okay. So they have provided in the Windows runtime a XAML class called Frame. And the purpose of this class Frame is for it to help you do the navigation. It's a frame that fills the entire window, and then you put other UI trees in the frame. Typically, only one UI tree at a time would be placed in the frame. And then the frame will take care of the forward navigation and the backward navigation on your behalf. Okay. Now, frame is derived from content control. Content control is derived from UI element, which means that we can assign a frame into this window right over here. And that's how we get our XAML user interface on the drawing surface, by doing that. Okay. Now, each frame object manages a collection of page-derived types. And I'm emphasizing types, because a lot of people, when they start working with this, they initially think it manages a collection of page-derived objects. But that is not correct, and that's not what you want. You want it to be a collection of frame-derived, page-derived types, not objects. And that is because we want the memory management to be very efficient. You also have to realize that Windows is being designed now to run on tablet computers that have very little RAM in them. Some of them have maybe only 1 gigabyte, or maybe if you're lucky, 2 gigabytes of RAM. So when you are building an application that's trying to work well on a tablet PC, you have to architect your application to be very memory friendly. So it's not allocating lots of memory all over the place. And what I'm about to show you here is how to architect an application so that it is very memory friendly and works well on a machine with small amounts of RAM. Okay, so on this slide, you have your app singleton class. This is the one instance where if you try to create a second instance, you get a catastrophic exception. So don't do that. But this is the app class that I was talking about. And that app class would have the frame that's a part of it. And the frame has the navigation state, which, as I just said a moment ago, is a collection of page-derived types. Now, another thing you're going to want to do is you're going to want to save some state for each page. In my example here, every page has some data on it. You know what? I'm being clipped off the left. How can I fix that? What if I put this here? Oh, he's fixed it? Oh, great. Then just go here. Fantastic. OK, good. So every page has some data on it. Like this has Kiev. And if I go back a page, it has Richter and Kiev. If I go back a page, it has Jeffrey and Richter. Now, this is really the same page type that I am creating multiple instances of. But the state or data that I want to have on each of those pages is different. So it lets the user believe that I have a set of pages that they're navigating through, but really it's the same page type over and over and over again, and somehow I'm just maintaining the state separately for each of those pages. So now, and that again is a very memory efficient way of doing it. So here's what I do. I defined a class that is derived from that base class, the XAML class page. Let's just call it page A. And when the user starts the application, I do create an instance of this page, and that instance creates the whole user interface tree, which has the text boxes on it, and the edit controls on it, and these buttons on it, and so on. That's part of the UI tree. Then I assign that UI tree into the frame, and the frame fills the drawing surface, and the user sees all these controls right over here. Now, I need to keep some state for the user while they're looking at this page. So the next thing that I do in my program is well, this is creating the page object over here. The next thing I do is I create a dictionary. And the dictionary contains strings for the keys and objects for the values. And then this dictionary object is where I'm going to store all of the user's state. So I have a dictionary. And in the dictionary, I have passed argument as a key that has Jeffrey in it. Actually, why don't we go to page 0, because right now this would be the first page. So it would have this string over here, main view launch activation would be the value in the dictionary for a key called passed argument. And then I have another entry in the dictionary called new text. That's the key, and it has a value of Jeffrey. And I data bind this to the dictionary, by the way. So as I'm typing in here the various characters, it just keeps updating the value in the dictionary constantly. So then, let's do this. So then the user says they want to go to a new page. So here's how I make this work when they go to a new page. When they click that button, I tell the frame to create a new page B. Now, in my case, I was using multiple instances of the same page type, but you might have different types of pages in your app. So let's say that instead of showing the user a page that has the same UI, we're showing them a page that has different UI, and I'm calling that page B. So this goes and creates a page B object in memory, which creates all the user interface controls, which is pretty memory intensive. And then I create another dictionary object here that has string object pairs in it, and I data bind this to the various objects here, so as the user's filling out the form, it's being saved in the dictionary information. But here's the part that's really cool about this. This can get garbage collected. So the old object, since the frame holds onto types, not onto objects, the object can now be garbage collected over here. And that frees up all the memory for all the controls that were on the first page that the user was looking at, and that makes the application be very memory friendly. Now, the dictionary I can't garbage collect. The dictionary has to remain, because that's the user state. And if the user goes back to the previous page, then I need to recreate all the objects for that page, and I need to put all the data back. So it gives the user the illusion that the page is in memory the whole time, when really the user interface elements get garbage collected, but the state that they have, that does stay in memory the whole time, so I can go and restore it. Now, the user might navigate to another page, and if they do that, let's say they go back to a page that looks like page A, so I tell the frame to go forward to a page A, it creates a new object Then I create a new dictionary, that I data bind that, and then the page B object, it can be garbage collected as well. So in memory, I never have more than the UI elements in memory for the page that the user is actually looking at. Now, if the user goes backwards, then of course, we just create one of these, re-data bind it back, and now the user's looking at the previous page. And then the other stuff could get garbage collected over here. All right, so that's the way that you should architect this, so that it's very memory friendly in the system. And that is what I was demonstrating over here, the ability to move backwards and forwards through here. And this, I didn't say this, but I'll just be really clear about it. So this is a list of dictionaries of string objects, right? So I maintain a list here of these things that allows me to go forwards and backwards through the list. Okay. That brings us to our next topic then, which is process lifetime management. So one of the things that Microsoft was doing with Windows Store applications is that they were looking at a lot of the problems that users have had with Windows over the years. One of the problems that users have had with Windows is that they could create multiple instances of an app. So if the user ran, let's say, Notepad, and then they put a bunch of information into the Notepad window, then the user switched away from to another application, they might not see the Notepad window anymore. And then a lot of times users didn't know how to get back to the Notepad window. So what a lot of users do is they would start Notepad again, which would bring up a new instance of Notepad and that's empty. Then the users would get scared and say, what happened to all the stuff I typed in? Right, so that was a big problem in the Windows operating system for the past several decades, actually. There's a lot of user interface issues related to all those Windows management. One of the nice things about Windows Store applications is because they're single instance only, whenever the user goes back to the start screen and starts an app, it keeps going back to the same app all the time. So the user will see the data that they still put in there. Another problem with Windows is that processes take a lot of memory. And if you start running lots and lots of processes, which some users do, then the system starts running low on memory. When the system starts running low on memory, it starts running much slower. In fact, if it runs very low on memory, then it starts crashing, and user interface elements start appearing as all black. You don't see text. You just get black rectangles on the screen. And then users don't know how to deal with this and how to fix it. Sometimes the operating system will pop up a little toast at the bottom that says the system's running low on memory, free up some memory. But then the user now owns the responsibility of deciding, well, to free up memory, what should I do? Should I close this application? Should I close this one? The user doesn't necessarily know which application is allocating the most amount of memory. So it makes the problem the user's, and the user doesn't really have enough information to correctly or appropriately fix the problem for themselves. So Microsoft wanted to improve this situation with Windows Store apps as well. With Windows Store apps, first of all, they're single instance, so it's a better user interface experience for users. The second thing is because they're single instance, they don't allocate as much memory. Right? If I ran 3 copies of Notepad, each copy allocates memory and then more memory. But if the Windows Store apps are single instance, they can only run once. That means you can't keep running it over and over and over again, allocating more and more memory each time. So that makes them more memory friendly in that regard. But they're also trying to say to users, you never have to close a Windows Store app. When you don't want to use an app anymore, just go and run something else. And the other app will just go and fade into the background, and it'll still be in memory. And the system has enough memory to handle it all. Well, how is it possible that the system could have enough memory for you to run 100 or 1,000 different Windows Store apps? The operating system owns the problem now of managing process lifetime. But you, as the software developer, you do have to do some work in order for this to work smoothly. So this is what we call the process lifetime management. When an application gets installed on the user's machine, it is in a state which we call the not running state. So it just got installed, and the application is not running, which means it's not in memory. It's not using any memory at all. Now the user can click a tile on the start screen, and now that will cause the application to enter what we call the running state. So now the application is in the foreground, the user is interacting with it, and the user can enter information into the text boxes and use the user interface and navigate throughout the app to the user's content. By the way, the operating system automatically shows the splash screen, right? If I come to the start and I want to, let's say, run the weather app over here, the operating system shows this splash screen immediately. This lets the user know that the operating system is starting the app. I'm sure you've seen in Windows too, where sometimes you double-click on an icon to start an app, and it takes a couple of seconds, and then you say to yourself, I wonder if it's actually starting. And then you're not sure, so then you double-click again, and the next thing you know, you have multiple windows up, right? Hasn't that happened to all of us at some point? So because the operating system now shows these splash screens, that gives immediate feedback to the user that the application has started, and the user knows. And the operating system does that, not the app. So that gives your app the ability to have some time to do its initialization too. Okay, so now on app activation, the operating system shows the splash screen, and then your application is in the running state at that point. Now, the user could switch away from your application because they want to go use something else instead. In which case, your application enters what is called the suspended state. And in the suspended state, the operating system suspends all the threads in your program. So your program is not allowed to execute any more code at all while it is in the suspended state. There are two reasons why the operating system does this. The first reason is if the user is not interacting with an application, by suspending the threads in it, those threads are not using CPU power. The CPU drains a lot of battery power, and Microsoft is trying to be very aggressive about building operating system and forcing applications on that operating system from conserving battery power so that users can use a Windows machine for many hours running on battery. So one of the ways that they accomplish this is they suspend all the threads for the programs the user is not interacting with. Because those threads are frozen, they can't run on the CPU, and therefore that drains less battery power from the machine. The other reason, the second reason, why they suspend all the threads for the background app is because they want the user to have a very fast, responsive experience with the application the user is interacting with. This is particularly important in a touch-based system as opposed to a mouse-based system. In a touch-based system, the user wants to put their finger on the screen and swipe, and you want the screen to be sticky with the finger. It has to move with the finger. It would be a terrible experience if the user put the finger on the screen, they moved their finger, and then the screen lagged behind it rather than going with it. So in order to keep the system responsive to the user, any application that the user is not interacting with, the threads in it are suspended, so that way all the CPU power that is available is given to the foreground application so the user can have a more responsive experience. So when an application is not being used, so more specifically, I have this list over here. So if an application is not visible, the user switches away from it, then the application enters the suspended state and all its threads are blocked. If the user locks the PC or the PC goes into standby mode, then the application goes into suspended state. If the user, of course, closes the application or logs off the machine or certainly shuts down the machine, then the application will go into the suspended state. And then ultimately it will die because you're turning the power off to the whole machine. Here's another nice feature, though. If the user is upgrading the application, let's say from version 1 to version 2, this has been a big problem with Windows in the past, but Windows Store applications fix this. If a new version of the application becomes available on the store, the operating system can download the new version of the app onto the user's machine. But what if the user is using the app at that time, right? That's been a big problem. Well, if the operating system can now suspend the app and kill it, install the new version, and bring the app back up. And this can happen basically automatically now, which was a real big problem with how to deal with this with desktop applications in the past. All right, so when any of these things happen, the application goes into a suspended state. Now, in the suspended state, the user could then switch back to the application. That would cause it to become visible again, and then it becomes back into the running state at that point. This would also happen if the user unlocks the PC or wakes the PC up out of sleep. Now, I can demonstrate this. Here in Task Manager, there's various apps that I have running on my machine, and there's a status column. If you try this yourself, by the way, you have to say View, Status Columns, and say Show Suspended Status. This is turned to hide by default. So I'm going to turn that on, and now you'll see that for some of these applications, they are in the suspended state. For any application like the Mail app that's in the suspended state, you can look at the entries here. Right? The CPU usage is 0, and that is guaranteed. Because the app is suspended, it is not allowed to use any CPU power at all. Now, the next column tells us memory. The memory is not 0 because the application is still sitting in memory, and it remembers its state. If the user switches back to the application, then the application will resume itself instantly for the user because it is still residing in memory. But you'll also notice that the amount of disk operations that it's performing and the amount of network operations it's performing, these are 0 because the threads are suspended. They're not allowed to access the disk. They're not allowed to access the network. And that's why they're 0 there. Okay. Now, if I switch back to the Mail app, I'll just move this to the side, and I'll switch back to it right over here. Oh, then it went away. But we bring it back. You'll notice that the word suspended goes away, because now I'm interacting with that application, so its threads are awakened and it's allowed to be doing things once again. And there was a little bit of disk access that happened right over there. And then if I switch away from the Mail app, it'll go back to the suspended state again after about 5 seconds. And here you can use this to monitor the thread suspension or not. Okay. Now, once you're in the suspended state, you could get terminated. The operating system reserves the right to terminate any application at any time now, any Windows Store application at any time. And your application will receive no notification of this whatsoever. So if the operating system decides to kill you, you just die. That's all there is to it. Now, why would the operating system choose to do this? Well, one reason is the PC is running low on memory. So now, if the PC is running low on memory, then instead of making it the user's problem, notifying the user, hey, we're low on memory, find some applications to go and kill, the operating system says, well, the system's running low on memory. I will not notify the user. I'm just going to go and kill some apps. Now, it won't kill apps that the user is interacting with, of course. So that would be very bad user experience. And it tends to kill the apps that are using the most amount of memory. So as a tip to you, the less memory that your application uses, the less likely the operating system will be to kill your app. The more likely it'll be to kill a competitor's app that the user is also using. Okay? So it's another reason to try to use as little memory as possible. The operating system will also close the app if the user says to Windows to close the app, or if the user does a log off or shutdown, that has to ultimately close the app as well. Also, the system will close it if the app is being upgraded or if it's being uninstalled by the user. And here's another one that's fun down here. When the operating system is suspending your app, it gives you a notification that it is suspending you. Once you receive that notification, you have 2 seconds to save some state. If it takes your app more than 2 seconds to save your state, then the operating system will just kill you. And the user will have to restart your app. So Microsoft's they're trying to be serious about this. They're trying to say memory management is important. You have to, as a software developer, you have to be serious about it and take it into consideration. And if you do not handle your state well and in a timely fashion, like if you don't let the system suspend your app within 2 seconds, then they say, well, then we're just going to kill you off. And then the user would have to relaunch your app. And this would give the users a bad experience with your app, which would encourage you to improve your application's experience in the next version. Also, you can go from the running state into the no running state. And this happens, there's some other rules. When the operating system displays your splash screen, then you have some time in your application to initialize to get your user interface visible to the user. The operating system actually gives you 5 seconds to do that. If it takes your applications more than 5 seconds to do its initialization, then the operating system will kill you. So again, really encouraging you to build a responsive applications that users will enjoy working with. If your user interface becomes non-responsive, let's say the user taps somewhere on the screen and then your application goes into an infinite loop, then the operating system will detect that and it will also kill you. And the user will have to restart your application and hope it doesn't happen again. Of course, if your application has an exception in it, like you throw some exception, then the operating system will kill you as well. The user would have to restart the app. And then the user could use other tools or utilities like Task Manager. I could always come to Task Manager, select the Mail app, and then say End Task here in the bottom right, and that will go and kill Mail instantly by doing that. Now, in order to play by the rules, since the operating system can kill your app at any time, what happens if the user is entering information into your app and then the operating system decides to go and kill your app? Well, normally, that's going to cause all your state to be destroyed. Then when the user tries to switch back to your app, the state is destroyed, and so you've lost all the information that the user has put in to the app. So what you need to do when the operating system is suspending your app, you are given this 2-second notification. You get this notification, and then you have 2 seconds to do some work. What you should be doing in that 2 seconds is you should be taking whatever state you have in memory, and you should be saving it to disk. Because the next thing that might happen is the operating system will terminate you. If that does happen, then when the user relaunches your application, you can know that you were terminated by the operating system. You can open up a file on the disk, reread that state back into memory, and then populate the user interface of your app so it looks exactly what it looked like before the user terminated, before the operating system terminated your process. And this gives the user the illusion that your application was running the whole time and was never terminated by the operating system. So the user ends up having this really good experience, and then for your app, but also a really good experience overall with the system, because the system is now managing memory instead of the user having to manage the memory. Okay, so to this slide here, when the operating system is going to suspend your application, it will give you a notification. And again, that's done to conserve battery power, and it allows the foreground application to stay responsive. And your application will receive a resuming event which I show here on this slide, this resuming event, when you go from suspended back to running, when the user brings you back to the foreground. The resuming event is important to applications that show real-time data. If you're building a weather application, for example, the user could suspend your app and then 5 days later go back and resume it. Well, if you're showing the temperature in Kiev in the app, you probably want to not show the user the temperature that was accurate 5 days ago. So when the resuming event, you would make a network request to get the latest temperature, and then you would update the user interface so you're not showing the user stale data. Similarly, if it's a stock market app, you might want to show the user most recent price for whatever stock they were looking at. Or if it's a sports app, you would want to show the user the most recent sports scores. So this is what the resuming event is for. It's a way for you to know you've been suspended for an unknown period of time. Then you can go and update your data, probably by making a network request, and then populate the user interface so the user doesn't end up looking at stale data. Now, for app termination, the reason why the system does this, as I said, is it frees memory needed by the foreground app, or this also happens to upgrade a suspending app from version 1 to version 2. And when this happens, your application will receive a suspending event. So you'll be notified that the system's about to suspend your threads. This gives you that opportunity to persist any user session state into a file on the hard disk so you can restore the state later when your application gets relaunched. And then usually people ask the question, So if my threads are not allowed to run when the user is not interacting with my app, but my app needs to do things in the background, like it might need to play music, or it might need to periodically make network requests because it's downloading files from the network, or maybe there's some code that I want to execute just periodically, like to check for instant messages or email messages or something like that if I'm building a mail app. How do I accomplish all these things if the operating system suspends all my threads? Well, in your application, you cannot accomplish these things. But Windows 8 does provide these other mechanisms that you can leverage to make these things possible. And I'm not going to go into these to great details, but there are ways for you to say to the operating system, here's some data that I want you to update my tile with periodically. And I want to be able to play audio in the background. And I need to be able to upload and download data even when I'm not in the foreground. And then the operating system will do it for you. So your code doesn't have to do it anymore. That's now built into the operating system. They also have a thing called background tasks that allow you to have some code that executes, let's say, every 15 minutes to go and check for something. So I'm not going to go into these other mechanisms in here because there's a lot of them and they all work a little bit differently. But Microsoft did think about these scenarios, and they did provide mechanisms available for you to leverage this. OK, so let's get back to the suspending and resuming part. So I said that when your application is suspended, you need to take your state that you have in memory and you need to save it to a file on the disk. So if you've architected your app the way that I was recommending, where you have this frame and the frame has the collection of page types in it, and then you also have this list of dictionaries that your application is holding on to, then this is the information that you need to save when your application is suspended. So we would take the information in the frame and we would write those types out to a file on the disk. And we would take our list of dictionaries in memory and we would write those out to a file on the disk as well. Then, once that information has been saved, our application can be terminated. The whole process can be terminated. Then, when our application restarts, when we're launched, we can look at the file on the disk. We can reload the frame state back in. We can reload the list of dictionaries back in, and then go to the rightmost page in the frame, create the page object that's brand new and fresh, show that to the user, data bind it to the dictionary, and now the application looks exactly like what it was when the user was last using it. All right, so I have a demo here, and then like the timing of this is perfect. Okay. So to demonstrate this, I have my application. That's this application here. Notice I have page 0 that had Jeffrey at the bottom, and page 1. Oh, I pressed the wrong button. That was really bad. So let me put Richter over here, new page. Now I'm at page 2. I'm going to put Kiev back over here. New page. Now I'm on page 3. So let me go back to page 2. And now, let's say the user switches away from my application. My application would get suspended and possibly terminated by the operating system. We can simulate this. In Visual Studio, I can click up here at Suspend and Shut Down. And this says to Visual Studio, simulate the operating system suspending my application and terminating it. So I will click over here. This raises an on-suspending event in my code. Inside here, I had a breakpoint set. Oh, no. Oh, catastrophic failure. There it is. Anyway, that was not supposed to happen. Let me try it one more time really quick. See if I can do this demo. Okay. Are we here? Okay, here we are. So because it terminated, all the state was lost. So Jeffrey, Richter, Kiev. Then I'm going to go backwards. Well, here, we'll do page 3. Nope, that was the wrong thing. Here. Let's get rid of that. OK, and then go back to page 2. So now I'm on page 2. Now we come back to Visual Studio. Click. All right, we're here. F10, much better now. OK, so this is a function that I wrote, and what it's doing is it's taking all the frame information and the list of dictionaries, and it is saving it to a file on the disk. That's what this does. So I am serializing all this data into a file on the disk, and this is the name of the file. Not that it matters. Now, when I returned from this method, you'll notice that Visual Studio stops debugging. My debugging session is over because the process was also terminated. But now here's the cool part. The process is dead. It is not running anymore at all. We could see in Task Manager, well, you don't know the name of the process, but it's not here. Okay? You don't see it here. That's because it's not running. But now I'm going to hit F5, which is going to relaunch the application. Now I have some breakpoints, but I'm just going to hit F5 to keep going. And now the application is up, but check it out. Right? I'm at page 2. Right? Even though I just relaunched it. That's because it reread all that state back in. So from the end user's perspective, it looks like the application had never terminated. And it remembers Richter, which I forgot the T, and Kiev, and it knows that there was a page 3, and that was it. But I could go back to page 2, and page 1, and page 0. And so from the end user's perspective, it looks like the application had never terminated at all. But I needed to register with the suspend and resume events, and I had to save the state and restore to state. On that note, we will be done. Okay, so I hope you enjoyed the session. Thank you very much. All right, and I don't know, I'll see you later. Go have a break.